and for the conference for inviting me back this year. This year, Marius and I taught a course. Marius is sitting here in the front row on packet mastering, some of the stuff I talked about last year. I'm sorry to say that none of the the things I'm going to be talking about are nearly as neat as some of the things, for example, that San talked about yesterday, or some of the things that Joanna talked about. So you're not going to learn how to break systems by listening to this talk. So hopefully you're going to find out new ways to think about large problems, and specifically how to kind of deal with lots and lots of data. So the title here, right, is basically about sifting big haystacks and trying to find the needles within that, the gems, if you will, and all those, and all that data that you have. I like this slide because it kind of illustrates the problem that we've had to deal with where I work and some of the data things that we work with. So a lot of people think kind of in the small when they think about data problems. They think about how you might, for example, deal with, say, a glass of water. So it's standing still, there's not a whole lot there. And if you want to analyze it, thinking about the scale of the problem is very, very small. And it's also a very static problem. Things aren't changing all the time. However, you wind up having to deal with kind of a flood of data, which is kind of indicated here on the right, flood of data constantly coming at you. It's kind of like trying to drink from a fire hose, right? So if you're using a way here. So this is, I think, a pretty good illustration of kind of the general concept here. So more specifically, the problem is not in gathering data. It's not that we did have some problems trying to gather lots and lots of data. It's kind of, what do you do with all that data? What's all the interesting stuff within that? So specifically, this came out of some measurement data that we did a couple of years ago where I work. We had instrumented a good chunk of the IPv4 address space in the internet. We were getting lots and lots and lots of requests coming in and trying to analyze new attack trends and new attack data. We can also kind of think about kind of spam problems or phishing mail, basically mail as a stream problem, or anything, even IM messages, right, as kind of a stream problem, trying to analyze those and find the interesting bits. What I'm specifically interested in is kind of find new signals that are kind of rising out of this, which might be coming from more than one source, more and more rapidly over time, which might indicate, say, malware being used widely. Or you can think about kind of a new attack tool that's been spread, and maybe some of the modifications that people are making to it. So the trick is to kind of find these scenarios and find these situations. So instrumenting a lot of address space to try and collect this is of course, a good idea. Problem is, if you're thinking about, for example, running grep over this, which is a regular expression pattern tool, you're going to run into some problems. If you're thinking about basically trying to read lots and lots and lots of files, you have some new problems thinking about here. It winds up being a needle in a haystack problem. Find me the indicators of new and novel attacks in a flood of data with lots and lots of signal there. There are a number of approaches that you can do to this. One of them, for example, is the Kalman filter from signal processing. It's a fantastic way to actually look at all sorts of interrelations within the data to find indicators that might indicate something that's strange happening here. Specifically, I'm thinking about, I'm going to talk mostly about string matching algorithms, string and fuzzy string algorithms here, and specifically in the context of spam. I like spam because I get a lot of it. So it's very, very easy for me to kind of constantly train it and test my new approaches out on this. But spammers are also kind of a slippery bunch. They're always changing their methodologies, they're always changing things to try and defeat static filters. And so coming up with kind of a new fuzzy filter is kind of the goal here. And finally, I have a lot of impetus to do this if I want to get rid of spam in my inbox. One of the research project that instrumented the large chunk of the internet, right, has been transferred to a project called the Internet Motion Sensor. And what they do is basically MD5 hash payloads that come in. This is great in some senses. If you get lots and lots and lots of the same pattern, it's always the same hash. You just kind of keep track of the same hash that way. However, if you have a very similar payload, you're going to wind up with very, very different MD5 hashes in this case. And they're going to look wildly different. It's not going to tell you that it's very similar. This is by design, right? MD5 is designed to highlight small, subtle changes and kind of cascade the change, avalanche the change, and highlight the fact very obviously to you. For us, however, this results in an explosion of hashes when we have similar payloads coming in. It masks the fact that we have similar payloads coming in, and things look wildly different. If you're an analyst, you now have to stop and think, how am I going to try and analyze thousands and thousands and thousands of payloads? So clearly the idea here is going to focus on the things that are similar. Find things that are dissimilar. It's not about finding things that are the same. And so what we're trying to do here is, again, detect new attacks. I'm going to talk, like I said, specifically, the good chunk of this talk is going to be on string analysis methods. Basically what we do is we treat a string of bytes, a payload, as a string of bytes. We can analyze it using a lot of techniques that are pretty well established, both within computer science and outside of it. This is great for things like plain text, which is going to be kind of the source of all my examples here. A lot of this comes out of my mailbox, and you're going to see what I mean by that in a second. Another very simple kind of illustration here. We're thinking about apples, oranges, in this case pears as well, right? And so people like to think about apples and oranges and kind of thinking about how much they're different. They're both fruits, clearly, but they look different, they're colored differently, etc. But if you look, say, in that bin of apples there, right? No two apples look alike, but you know that they're apples because they're very similar to each other, and they're both basically apples. Pears look different than apples, look different than oranges, but no two pears, no two apples, no two oranges look alike. Similar is the key here, so keep this concept in mind. Classically, what people do when they're looking at basically analyzing payloads as strings, they're looking for things like substrings. Try and find me, for example, the occurrence of, say, /bin/sh in the case of an exploit. Try and find me that. Or try and find me null bytes or no-op bytes in the case of an exploit. They can do this through substrings, they can do this through regular expressions, and they can even, like I said, hash payloads. There are 4 major problems that I highlighted here, but these kind of are like high-level problems. So the point changes within this are going to obviously cause problems. So if an attacker, for example, notices that you're looking for bin sh, starts firing up bin csh, or bin bash, right? Clearly there's going to be a problem there. You're not going to be able to match on that. Regular expressions which people might use to actually look for that are going to fail because they're Boolean. Things either match or they don't match. There's no score associated with, well, it almost matched, or this match is much tighter than another match. So while regular expressions are very powerful, and you can write very complicated regular expressions, ultimately they're still Boolean, so you have a difficulty kind of finding slippery string matches. You also fail to detect kind of the small changes, the subtle changes within things, point changes. Again, these are sometimes insignificant, sometimes very significant, but you have difficulty kind of identifying those in those situations. And lastly, if you're trying to match, for example, all possibilities of phishing emails, you end up with a very large, very complex regular expression, which is difficult to kind of edit or analyze. It can be automated to generate it. In many cases, people try and hand generate those. So you have these very, very complicated expressions. So this is going to talk about a lot of simple ways to actually achieve much of the same thing. In this case, the key example that I keep using in all my slides is Viagra. Viagra is a common piece of spammers' email, right? They're trying to mail you to try and entice you to kind of come on by their pharmacy and buy Viagra online. So on the left is kind of the canonical Pfizer logo for Viagra. On the right are several different forms of how spammers try and present to you the term Viagra. You're looking at this and you're thinking, well, it's not quite Viagra in most cases. There's a couple of times I spelled it correctly. But overall, they all look very, very similar to the real word Viagra. Your mind puts it together as being very similar. And we're going to talk about how we can teach computers to do the same thing. If we hash all of these using MD5, all the hashes look wildly different. If we look on the left, things look more or less similar, right? There's some insertions, there's some subtle changes here. People insert a dash or an underscore or a dot, even a comma in one case, right? They make an A to an at sign, change. The hashes clearly indicate this to you, but they don't indicate the fact that this is all basically the same word. So what we're going to try and do is use this very simple example as kind of a generic example, a general example of how we can find similar payloads in all of this, right? So there's multiple ways to discover these similar payloads here, and we're going to focus on two major ones here, suffix trees and string distance functions. I have some code that I wrote to do string distance functions and implements a number of popular and well-established algorithms. Suffix trees, the examples that I point out come from a library from a graduate student in Cambridge in the UK, libsuffixtree. And very powerful, very fast library, so that's also widely available. Each of these methodologies have their own weaknesses and strengths, and hopefully I'll highlight kind of where they're appropriate to use and where they're inappropriate to use. This basically comes from my background. So I'm actually a trained biochemist, and so I looked at basically the sequences of bytes here and thought, oh, this looks very familiar. It looks very familiar to me, right? If we look at DNA, if we look at protein sequences, they're all basically strings of bytes, right? String, 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 and basically you can do a number of analysis. You can do a lot of analysis on these using, again, high performance, well-established algorithms to find the similarities and to find the kind of root common things within all of this. So if we simply think about string alignment techniques, if we think about string similarity techniques that come from that, it makes a lot of sense. On the bottom here is a piece of a figure that I think illustrates this pretty well. If we look, the first row here, which is not highlighted, is just called the consensus sequence. When a researcher basically expresses what's called a consensus sequence, it is the expression that more or less describes with much similarity, with the kind of the core similarity, everything that you're going to find there. Uppercase means it's always a match. Lowercase means it's usually a match, and a dash in this case means it's usually not a match. So we can see here the lowercase I, capital G, lowercase l, lowercase s, uppercase v, etc. in the consensus sequence. And if we look here, we have two clusters, or two basic groups of data. The first is 4 short pieces of a sequence from 4 different genes, or proteins rather, showing on the left the starting position of this, and then kind of how it's aligned. So the blue shows an exact match, purple shows another exact match, and if it's not highlighted, it's different. If it's red, it's kind of interesting as well. But you can kind of see how this visually lines up, and how you can express what kinds of things line up. In the bottom, we have another sequence, which kind of lines up, but isn't quite as strong a match to this as well. And it does very, very poorly against the consensus sequence here on the top. This is kind of the basics of and core of what bioinformatics does a lot of. So analyzing DNA sequences and protein sequences using techniques and algorithms to basically give them alignments like this, which can help them, for example, classify gene families, classify protein families, find the interesting bits that might have functionality, it's so on and so forth. So we're going to take our cue from this and look at string algorithms, which might do the same here. For example, right? Treat the payload as a sequence of bytes, align and find our similar inputs here, cluster around them in the future, and find the consensus sequence that kind of describes this. So if we look back at our Viagra example, you can kind of see how this all works. The last position is usually an A, sometimes an ampersand, and once a space. First position is usually a V, either capital, lowercase, etc. How we can kind of achieve the same kind of thing that we achieve in bioinformatics by thinking just about generic strings and what they mean. Suffix trees are a data structure and an approach to trying to do this by basically building up what's called a tree of strings, basically starting from the string's root. And whenever a difference is encountered between either the root or a pair of strings, you introduce what's called a branch, one for each of the 2 different strings. This is implemented in a library from Christian Kreibrock at Cambridge called libsuffixtree. I've written some bindings in Tcl and Python as well for it, so you can access it in a scripting language, which is pretty convenient. But basically what you do is you load it up with a series of strings and you ask it to kind of find the interesting bits within it. It builds a tree and it produces out things like the longest common substring out of that as well. To illustrate this, I'm going to use 3 sample sentences. She sells seashells down by the seashore, and by the roadside. We can see that the first part is usually the same. This is going to be a great root, but then we have some differences. And this is how we illustrate those using a suffix tree. We have a root, so the first 4 words of the sentence, she sells seashells. Now we have a branch, down by the seashore and by the roadside. And we're 2 different sentences here, differ from this root sentence that we have here. So we've introduced branches. You can see immediately the power of this, right? So we basically reduce the complexity of our data here. We have a long common substring here. She sells seashells. We have some differences. But there's also some problems within this, almost immediately apparent. Whenever you have a difference, you branch, and you never return to the root. So in this case, the first sentence here, and the second sentence, right, differ by the introduction of the word down by the seashore. The second part of the sentence, though, is exactly the same. That's just fine, right? And it should return, in theory, just highlighting the fact that we only introduced a simple word here, down. That's how they differ. The second and third sentence differ quite a bit, by the seashore and by the roadside. And there's a significant difference. But basically, we have a problem here with suffix trees. We get infinite branching, no matter what we have here. It's great. It's fantastic for things that have a lot of common roots. So for example, if you look at a lot of URLs that you might visit on a single site, they often have a common root to them, right? And some pieces might change. Or if you look at a lot of malicious requests that might come into a web server. Again, if people are changing arguments on the tail of the request, you can find the common root and maybe highlight what the problem is there. Reducing the complexity, but you might have a few problems there. So it's not always appropriate to actually use a suffix tree. String distance functions, however, are kind of a generic approach to this, which solve a couple of the problems there. So there are many popular functions, and they basically calculate what's considered to be the cost of converting from one string to the next. They operate pairwise on 2 input strings. And basically, counting number of transformations you have to go from one to the next. Depending on the algorithm, the cost is calculated differently. It can be a flat cost to insert or convert a character. It can be variable cost. It can tolerate certain things. But they all have their place because they all don't work in the same scenarios here. And we implemented several of them in a library called libdistance, which is available on the website. We introduced this last year, and yesterday I actually rewrote the Python bindings for it. The canonical edit distance function, or Levenshtein distance function, operates by saying that every change, whether it be an insertion or a conversion, is a simple unit cost of 1. So basically, when we have to change a character to go between 2 different things, we basically minimize the cost to try and align our 2 strings here. We now see our two sentences here, which handle using kind of a low-cost insertion here, 5 characters, DOWN space, to insert and modify the 2 sentences. So these are very, very similar here. And the reference to the actual paper which introduced the algorithm is shown there on the bottom. But going clearly from our suffix tree, which had some problems, we can see how you've more or less returned, if you will, to that root, that common sentence here, and simply tolerated a simple insertion of the word down. There are some weaknesses here, however. If we go back to the example of Viagra, right? Your mind tolerates a very small change here, right? The A to the at sign. That's fine. Levenshtein distance, however, calls this a unit change. So it associates a cost of 1. In this case, Viagra to V1 at Gara, right, is a change of 2. I to a 1 and an A to an at. But really, they're more or less identical for most purposes, right? They're very, very similar. So clearly, we have some problems with this function, with this approach already. So it doesn't work very well for spam. It doesn't work very well for a number of things which tolerate similarities here. But not all similarities are equal. So not all insertions really are equal as well here, right? So to go between the word Viagra, which has a single space between each letter, and Viagra, but with 4 spaces, or 5 spaces rather, between each of them, is a cost of about 20. However, to go from the word Viagra to Welcome to KL Malaysia is also a cost of 20. So if you try to compare them and try and find out which ones are most similar here, you basically have a problem. Spammers rely on the fact that visually you can tolerate the insertion of white space to reassemble the word for yourself. But clearly you can't express Viagra by saying welcome to Malaysia, right? However, the function basically points out that these are basically the same transformation and they have a cost of 20. So if you're relying on the function to kind of highlight those differences, you have some problems that you're going to encounter. The Hamming distance function is another canonical function that does this as well. Basically does a point-by-point comparison of each of the two sentences, and each difference yields a cost of 1. The restriction on this is that the inputs must be the same length, or at least the pieces that you're going to cover, right? So you can have two different variable size strings, but you can actually associate different, you can basically say, find me the differences only in the small piece of each of them. So here's our simple example. I introduced some typos. She sells sea smells down by the seashore, which are much different than seashells. Hamming distance cost is 1 to convert from shells to smells, right? Which is fine, they're pretty similar. It's very useful for detecting very small point changes here within a large data set, but not terribly useful overall. If you have an early point change, however, you have problems in this. So here we change the gender, and we change shore to shores, and we have a Hamming distance change of 35 here. These sentences are very, very similar, but there's only been 2 small changes here. We've moved the S from the front of the sentence to the back. But because it can't align them at all, it simply does a point-by-point, space-by-space comparison, we have real problems. And it doesn't deal very well with very similar characters in the case of, say, an A to an at sign, like we see spammers use, or misspellings, like I often make. Then we have some real problems here with the Hamming distance function. Damerau distance function is very, very similar to Levenshtein of the edit distance function, right? And with the major difference is that it tolerates a swapping of the adjacent characters. So it's a very common typo to make. I often make it myself. And so here we basically can tolerate that by basically noting that and saying, oh, it's a minor change. We'll be okay with that. So it's great for misspellers like myself. And here we have our 2 sentences here. And I mistyped one of them, and it says SE space A shells instead of seashells. And it shouldn't, and the Damerau distance function says the cost here is 0. The Levenshtein distance basically says it's a cost of 4 to make a number of changes there. Oh, and the and to seashore, right? So 2 typos in that, as I'm prone to making. Damerau tolerates these, says it's basically the same thing. Levenshtein, however, says their difference is 4. Now, we can also associate variable cost for each of these 2 operations, conversion and insertions. And we can actually, and this is an algorithm that comes straight out of bioinformatics, the Needleman-Wunsch distance between two strings, or two inputs. What it does is it basically lets us correct some of the deficiencies that we find in the edit distance function, because we can now associate costs with each of these 2 operations on a per source and destination basis. So the cost, for example, to convert from an A to an ant sign is 0.1. So it's not 1, it's 0.1. And the cost of going from, say, an A to a B is 1, right? Because that's a significant change. So going from Viagra to V1 at Gura is in fact a cost of about 0.3. So we made 3 small changes here. There's a number of things you can do, I to 1, et cetera, and so O to 0, and things like that. That's kind of the key thing there. All these methods still fail, though, when you have very, very sweeping changes across them. And so if you have, for example, chunks of the sentence that can be swapped around in place, these are going to fail horribly because it's going to look like wildly different inputs. It doesn't know how to take pieces of them, kind of move them around, if you will. So she sells down by the seashore, and down by the seashore, she sells seashells, right? Same basic sentence, but we swapped halves here, right? We have big problems. In the case of network security, polymorphic attack payloads are going to fail here, or when we actually have payloads that can actually tolerate basically swapping around orders of operations. We're not going to be able to identify them as being similar, or things we've seen before, things that we're on the lookout for. So I mentioned the output to these. So suffix trees spit out the longest common substring. So in this case, and our simple example would be she sells seashells. And string distance functions return that cost, right? So the cost to convert from one to the next. It's useful to cluster payloads together. Basically, to cluster, you more or less find all the distance between them, pick some centers in the case of k-mean clusters, and find things that kind of group around that until you're basically done finding new centers of clusters. The beauty of clustering is that you go from thousands or millions of inputs down to just a handful of things, and you can basically classify things by how similar they are. The longest common substring approach is pretty useful, like I said, for things like URL analysis. When people are attacking, for example, a web server that you're looking at, you can find the root URL that they're trying to attack. For example, it might indicate a script that they're trying to attack. It might indicate a methodology that they're trying to attack, and basically different things that they're doing within that. The distances between the two payloads lets you, for example, classify spam and indicate, for example, a phylogeny tree, a family tree, for example, with spam. Lets you identify mutants of the spam, lets you identify mutants or malware in some cases as well. So if we look here at the simple edit distances of all of our Viagra changes here, we've normalized the case. Case doesn't really matter all that much, right, in this case. So Viagra to each of these different variants, you can see the edit distance costs here. And some of them are kind of high. So Viagra, for example, the VI _ at GR at has a cost of 4 to make 4 different changes there. When we create, for example, a spam-friendly cost matrix for our modified function, which allows us to change the variability of these costs, we have conversion costs have a specific cost of 1, unless it's specified to be different. Insertion cost is pretty cheap, though. If you want to insert, for example, space or dots or whatever, that's pretty cheap. An I to a 1 is, again, pretty cheap, etc. What we wind up with is, since a little more revealing here. So Viagra, all these different variants of the word Viagra, right, to all these other different variants, we can see which ones are very, very similar. So we have so the lowest cost one here, I think, is on the bottom, but much more revealing, I think, than the simple edit distance between them, showing us kind of the power of how we can actually do this here. Excuse me. So using spam, right, the reason I like spam is because it's much easier for me to get a hold of lots and lots of spam than it is to get a hold of lots and lots and lots of attack payloads. So I can work on this at home, I can work on this on the plane, etc. I have about 4 or 5 years worth of spam payloads stored around my house just because it's fun to analyze them. The biggest things I found are that there are some implementation inefficiencies here, right? So if you actually look at the code that does the Levenshtein distance or the edit distance function, right, it allocates huge chunks of memory to basically load this cost matrix to find the minimum changes here. And we wind up with this very large one-time memory footprint, which can be a real problem if all you're running it on is a laptop or all you're running it on is kind of a low-power system here. Currently, what we do then is kind of find the popular payloads and periodically analyze them to try and find the interesting ones here. So there we can kind of tolerate it. Trying to do this in real time is actually pretty slow because of the amount of memory overhead that you have, unless you have a lot of computing power at your hands. What I haven't done yet, though, is built up a cost matrix for binary payloads to tolerate, for example, insertions of null operations, for example, in the right place and things like that. But what I can do for now is basically find interesting spam things, spams that are related to each other. So I've released the libdistance code. I wrote it with Evan Cook as a graduate student, actually working on the IMS project. So we have the code up and available. Currently what's up there is 0.20, and I actually finished up some stuff with 0.21 last night with brand new Python bindings, which are much more efficient. libstree is available on Christian Carbach's site at Cambridge. So if you guys want to download these and play with these, they're pretty nice libraries. So what can you do with this, right? So you can, like I said, you can analyze spam. You can also basically generally sort your mail, which is a kind of a neat little function here, right? So you can kind of find the things that are interesting. This is sort of different than what you might find as Bayesian analysis, where you can now basically do naive sort of training on this, as opposed to kind of having to basically pre-train it and say, this is what spam generally looks like and everything else is fine. You can analyze HTTP requests, as I mentioned, which is a pretty fantastic way to find variants of, say, code red, or find variants of new SQL injection attacks, things like that, or just generic log file analysis. You can take your syslogs, you can kind of find sort of the canonical lines or the canonical elements that you want to look for and find things that look very, very similar to that. basically saying, for example, it doesn't matter what the host name changes, what matters is that the disk is full, or that the box has crashed, things like that. One of so there's a very related library for Java called Second String, and the author is a professor at university, and what he's done is between the Second String library and a couple of other things, he's actually been able to sort his mail automatically based upon how similar it looks to a mailbox that he's created. So instead of doing Bayesian classification, it basically finds the generic mail, the description for that mailbox, and sticks mail in the correct location. Sort of a different approach than what you might find with a Bayesian approach, but it's a little more powerful as well, because you can do all sorts of basically fuzzy matching here. So Python bindings for lib distance are pretty easy. Here we have 3 different strings. We basically import our distance module, and we basically print out the Levenshtein distance for each of them. So as string 1 and string 2, string 1 and string 3, we can basically get out some distances here. To do the needle and Wunsch distances, we can basically create a matrix, M. We can set our insertion costs, we can set conversion costs as well, and then basically print out the distance here. And then we're done with our object, and we're ready to go. The other thing that's a neat way to actually look at a lot of this is to do basically graph comparison algorithms. Now, I had nothing to do with building this, so don't get the wrong idea, but it's a very useful technique for actually classifying pieces of software that you find out there, or for doing things like binary differences and things like that. This is how people do bin diff. Basically, you build a call graph of an executable. So this can be a normal piece of software, this can be a piece of malware. Now, when you get a new version of this, either through patching or through an attacker modifying the payload and sending it your way, you now generate a new call graph. So you have 2 call graphs. And using graph isomorphism approaches, you can basically compare the 2 graphs and find the differences between them. This lets you do things like build up families of executables in the case of malware. So if you've identified who you think might have written a piece of malware, you have a new variant of that, you don't even have to decompile it. You can just basically do call graph analysis and say, well, it looks like this person's made a few changes. Who wrote what versions of Zotab, who wrote what versions of MyDoom, and so on and so forth, because these patterns change between them. And so people will hook in, for example, different functionality. Different groups will hook in different functionality. Here's a simple call graph for a very basic program. It starts in one path that basically does an open and a read and a close. And the second path is much simpler, just an open and a close, and then finally you write out some data. So a very simple call graph showing nothing terribly fancy here, but kind of gives you the idea that, it basically presents the idea. So it's a directed graph. You have 2 endpoints and a directionality between them. You can build it based upon call and return structures from things like ktrace or strace. IDA-Pro also builds these on Windows, which is a fantastic tool. And you can do this actually, pretty much real time or whatever. Very, very simple scripts to process the results and build up these graphs. Todd Sabin has written, this is actually a figure from Todd Sabin's paper, has written a fantastic paper describing how you actually find differences between 2 graphs. And this lets you highlight these differences. So for example, when you get a patched binary from Apple or from Microsoft, you can now find what's changed. So here, everything in green is okay, it's the same between the 2 of them. Gray or blue in this case is the old stuff, and red is the new stuff. And you can basically highlight new patterns of call usage here. And that's a very, very simple and very powerful way to do this. And again, the reference is down here on the bottom. But what you can do, again, is analyze binaries. You can say, well, when Apple patched this, what they actually did is they shut off this code path, but they've introduced a new code path. So in the old version, right, we basically have to traverse these functions to get to our exploitable condition. In the case of malware, you can look at this and you can say, well, there are 3 changes to go from one piece of software to the next, but there's 10 to go between the first piece of malware and this third piece of malware. So the first 2 are probably the most similar, and you can basically group them together that way. Lets you very, very simply analyze your software this way and find all sorts of interesting things. BinDiff, I think, is a plugin for IDA-Pro. There's also a standalone version of that available. And then Todd Sabin's methodology is described. Very, very easy to read the paper and implement from there. So that's it. Like I said, nothing terribly exciting compared to some of the other really cool talks I've heard here. But I do thank you very much for your time and for your attention, and I'm happy to take any questions at this point.
How is compared to the neural network? Because you know neural network, it compares the pattern.
Mm-hmm.
How is it? Is better or?
So the question is, how does this compare to neural networks? I'm actually not as familiar with neural networks as I should be to be able to authoritatively answer that question. From what I do know and from what I have done with neural networks, this is significantly easier to do than neural network analysis, which requires a lot of training and a lot of horsepower to basically find basically the patterns within the data here. Here, this is much simpler, but it's probably not nearly as powerful as the kind of output you can get from neural network analysis. This basically helps the analyst reduce the complexity of the data set that they have in front of them. So instead of looking at millions and millions of lines of log file lines, for example, they're looking at, say, maybe 100 different families of log events. You can achieve that with neural networks, but this, I think, is easier probably to get to a certain point, and then it leaves the onus on the operator now to do some more analysis upon that. This is the core, though, of basically a three-stage process where you gather data and find out the distance between them, build some clusters, and then find the consensus data. So now when you actually get new data in, you analyze the new data against the clusters of the data to classify it, as opposed to analyzing against all the other things. So hopefully that answers your question.
Yeah, you also mentioned Bayesian filters that are in widespread use today, I think, for spam classification. Can you explain a bit more detail where you see the difference in using the lib distance approach and analyzing compared to the Bayesian filters? And second question, you mentioned that lib distance might also be helpful to analyze HTTP requests. Can you give some examples of what this might be and what can actually be found?
Sure. So the first question is, how does this compare to Bayesian analysis, or how could it complement Bayesian analysis? Bayesian analysis specifically has become very popular for spam classification, where the program builds a training set of tokens that appear, so words that appear in emails, and these can appear in normal mail or spam or anything. And basically, you assign a probability, a bucket that source, that corpus of data belongs to. In the case of spam, for example, you basically say, this is a spam training set, take all the tokens, and those are tokens for spam. Take all the pieces of the second corpus and call that normal mail. The Bayesian program will look at the probability, the frequency with which these tokens will appear in either of the two buckets, and assign a probability that it belongs to one bucket or the other on the basis of how frequently that token appears. How should I say that? It's a very powerful technique, and it's pretty fast, and it's become very widespread for a number of reasons. One of the problems that you can encounter with it, though, is you wind up with this huge list of tokens that might change over time. And so when a spammer changes what words they use, or how they describe the same word, in this case, Viagra, your Bayesian program isn't going to know how to classify it. It's going to look at it, it's going to say, well, it's not the word Viagra. I don't know what it is, so therefore, it's not a token that appears in spam. Using a distance function like this, you can say, well, it's not exactly Viagra, but it looks very much like this token that appears 99% of the time in spam. So it's probably the same thing. It's probably a spam token. So you use that to weight the mail and basically pull it over towards the spam bucket for classification. You use more than one token, clearly, to classify things. But that's, I think, the benefit of this. Instead of doing exact matches, you can now do fuzzy matches against these. Could certainly extend Bayesian filtering. Could you remind me of your second question? The HTTP examples, yes. So let's see. Right, so I'll fire up Python. Does it show up very well at all? Can we get the lights dimmed down for a second? I think that might be a bit more clear. So. Thank you. for our distance function. Is that clear to everybody, the white text in the blue background? So if we have our first string, so get CGI bin film.pl arg equals cat etsy password, and string 2 rather is, I'm clearly doctoring these up to kind of illustrate my point, but hopefully it'll work to illustrate my point. So if we do now distance, no, let's make a third one here. Okay, so oops. So third string. So we have string 1, string 2, and string 3, right? And if we do S2, if I spelled it correctly. So there's a distance between string 1 and string 2 of 12. String 1 and string 3 has a difference of 33. And string 2 and string 3 has a difference of 26. So what this tells us is that string 1 and string 2, so get CGI bin vuln.pl arg equals blah and arg equals blah, are much more similar than get index.html. Is that better? Okay. So this is the outputs that you get from this, and you can use these now for functions, right, to kind of analyze. Well, you know, what's the common thing here, right? So if we make a string 4, so now if we look at the distance between string 1 and string 4, right? Again, low-cost distances here. I haven't yet swigged up the bindings for Python to libsttree. I was working on it this morning. But clearly, thinking about suffix trees, right, this will highlight the fact that you now have this common root here, which is going to be get CGI bin /vuln.pl. That's the common argument there. One of the strategies that I use to actually analyze things like this is to say, let's give it a cutoff filter or tile. Dump these all into a suffix tree, find the common substrings of those, and highlight kind of the core piece of that. That's the basic workflow that I use there. The tools aren't very mature, like I said, in respect to kind of tying them together. It's a lot of handcrafted scripts when I analyze them, but that's kind of the core functionality and the core process there. So hopefully that looks interesting and useful to you in that respect, and hopefully answers your question as well. Marius?
So I think you mentioned that libsttree could find the longest common substring for you.
Right.
And I was wondering if that actually uses suffix trees, and if it does, how does it work?
How does libsttree?
No. I was wondering if the LCS algorithm in libsttree actually uses suffix trees. And if it does, how does that work? Because it seems kind of suboptimal to me.
It seems, kind of what to you?
Suboptimal.
Suboptimal?
To use suffix trees for longest common substring. I was just curious.
Basically, libsttree does use a suffix tree, as I understand it, uses a suffix tree to spit out the longest common substring. What you do is basically build a little pile of strings, you add them to the set, and you basically build what's called a suffix tree out of that set. And you find essentially the longest branch, which can be the root branch or a core branch of any of those. Basically the longest run that you have that has more than 2 strings associated with it, or more than 1 string associated with it. So it's the common between more than 1 string. So in building that suffix tree, basically you anchor and you run down and find differences and introduce a branch.
That's going to miss things where you have
That's what I pointed out earlier, right? So it's poor man's LTS, yeah, basically. But it's for things that have, like, you know, in the case of URLs, right, or URIs, it has a common kind of base to it that makes a lot of sense. So it's not applicable to everything. Any other questions? Well, again, thank you very much for your time. I appreciate it, and hope you guys have a good day.